In this video, we're going to look at some examples that demonstrate the application of the stationary phase method. So we've got these two integrals here for which we are going to want to derive the leading order expression of approximating these integrals as lambda goes to infinity. So first I'm just going to rewrite the formula that we derived for the asymptotic approximation of integrals of this form. So let's go on with A. So in A we are going to write our integral as the real part, because it's the cosine of the integral from 0 to 5 of e to the I lambda times 12t minus t cubed. This is all divided by 2 plus t squared dt. Then our phi is going to be 12t minus t cubed. So phi prime is going to be 12 minus 3t squared. The second order derivative is going to be minus 6t. If we equate first order derivative to 0 and solve, we get plus or minus 2, but only the positive one lies in our interval of integration. So this is telling us that t naught is going to be equal to 2. So f of t naught is going to be 1 over 2 plus 2 squared is 6, and phi of t naught, it's going to be 24 minus 8, and then second order derivative at t naught is going to be minus 12. So then we're just going to plug into this formula here to get the asymptotic expression of our integral. So I of lambda is going to be like 1 over 6 e to the I lambda times 16 minus I pi over 4. Remember, we said that this sign here always occurs with the sign of the second order derivative. Then here we're going to have 2 pi over 12 lambda. Okay, and so this is just going to be 1 over 6 square root of pi over 6 lambda cosine 16 lambda minus pi on 4. Now this, using trigonometric identities, can be recast in the following form. So it's going to be pi square root pi over 12 lambda times 1 over 6 into cosine 16 lambda plus sine 16 lambda. Just make sure that you can work out how that comes about. Okay, Then in number 2, we have the integral from 0 to 4 of the square root of 1 plus t times the exponential of I lambda into e to the power t minus 2 minus t dt. So in this case, phi of t is e to the power t minus 2 minus t. Phi prime is going to be e to the t minus 2 minus 1. Phi double prime is going to be e to the power t minus 2. Then equating this to 0 is going to give us so phi prime equal to 0. So this is going to be 0 if this is 1 as well. This is going to be 1 if the exponent is 0. The exponent is going to be 0 if t is equal to 2. So that means the our t naught is going to be 2, which is in the interval of integration, so that's fine. So f of t naught is going to be square root 1 plus 2, square root 3. Phi of t naught, so if we plug in 2 there, we're going to get negative 2. And phi double prime at t naught is going to give us 1. Okay, and so what this means is that our integral is going to be like as lambda goes to infinity, square root 3 e to the I lambda times negative 2 plus I pi over 4. It's positive this time because the second order derivative is positive here. Then there's going to be times square root 2 pi all over lambda, because the second order derivative is 1. So tidying this up is going to give us 6 pi over lambda square root of e to the I pi over 4 minus 2 lambda. So that's going to be your asymptotic expression approximating this integral for large values of lambda. Okay, so that concludes number 1. Let's now go to number 2. All right, so in this question we're going to look at the Bessel function. So we're going to use this integral definition of the Bessel function to derive a leading order asymptotic expression approximating J naught for big values of x. Okay, so the first thing to do, let's just use this to write J naught. So J naught, so all we're going to do is plug in 0 where there is n. So that's going to be your integral from 0 to pi. So this term is basically going to disappear. So it's going to be cosine of x sine theta d theta. Right, and then we're going to write this as the real part of 1 over pi, the integral from 0 to pi of e to the ix sine theta d theta. So if you like, in the format of our formulas, the role of lambda is played by x this time, and the dummy variable which we had as t is theta this time. Okay, so what we are going to do is we're going to write phi of theta. So phi of theta is simply going to be sine theta. The derivative of that is cosine theta, and the second order derivative is negative sine theta. Then we need to equate the first order derivative to 0 and solve. Now in the interval 0 to pi, cosine theta is going to be 0 only when theta is pi on 2. So that's going to be our theta naught. Then our phi at pi on 2 is 1, and our second order derivative at theta naught is negative 1. F is 1, so f of theta naught is always going to be 1. So what this thing is telling us is that J naught as x approach infinity is going to behave like the real part of 1 over pi e to the ix minus I pi on 4, and then we are going to have 2 pi over it's going to be x times the absolute value of this is just 1, and then of course this is just going to be the square root of 2 pi over x times cosine x minus pi over 4. If we use the trigonometric identities, again we could rewrite this. It's going to be pi over x into cosine x plus sine x. So that is the asymptotic expression of J naught as x goes to infinity.